Hello, everybody. I'm Marco Capaldi from IIT, the center in Torino, and I'm here to show you some achievement we did with SMAC, which is an European project devoted to the smart system co-design. And my presentation of today will regard hardware in the design for wireless sensor network based on impulse radio ultra-widebands, okay? So basically, we are talking about an European project which is called SMAC, okay? Smart System Co-Design. And why it is important to consider smart system co-design? Because as you can see from you know, all the things that you can have around, smart systems are taking place more and more in everyday's life. What does it mean? That we're not talking about just embedded systems. We are talking about intelligent systems with a lot of functionality and, most important, heterogeneous functionality, okay? What does it mean? It means that if you think about 30 years ago, when you could consider, for example, a microprocessor, a computer, or something like that, that was just a purely electronic component. Now, if you think about cell phones, for example, what you can have is something that is completely heterogeneous. Okay, we had keyboards 30 years ago or something like that. Now we have touch screens. We have health sensors, for example, all merged together. So now the most important point for an electrical engineering point of view is to merge these different worlds together so that we can design smart systems efficiently. What does it mean? So maybe you have experience with some, let's say, design, right? You guys have some, let's say, expertise on CMOS circuit design, IC design, MEMS design, microfluidic design, for example. But now, since the systems are getting more and more heterogeneous and need to be tightly optimized to a specific application domain, what needs to be done is to merge these different worlds together so that at design states, okay, when you are in front of your computer with an electronic design tool, you are able to consider all the different aspects related to each domain, microfluidic, for example, MEMS, electronics, and of course, RF electronics, and of course, digital electronics, and of course, mixed signal electronics, all together so that you can optimize completely the system. In fact, the Smart System Co-Design project talks about abstraction technique applicable to diverse classes of electronic subsystems. You have done mixed signal and analog design, digital design, for example. And these are different words because, as you might know, digital is a graded, let's say, analog function. Analog is in continuous time domain. Digital is in discrete time domain. But we need to match all these words to have a tightly optimized system. Second thing, of course, if you want to match the worlds, you have to think about parametric models which enable simulation speed up and solution space exploration so that it's not just a matter of pointing and click operation and use your mouse to just find something that can be maybe algorithm based to come out with the results of an optimization. But of course, what you need to do is to understand that you have a model and you put it in a complex co-simulation. We are talking about co-simulation, simulation of heterogeneous systems, okay? And of course, since market is continuously demanding MEMS, microelectromechanical system, as you might know, what we need to do is to merge these different worlds. Of course, MEMS are in the mechanical domain as well, and they come out with the electrical domain, and the other way around as well. But we need to merge these different worlds, okay? So, this is a constraint-driven methodology we have achieved. You see all these kind of blocks you can see here in the slides to show you what can be the heterogeneity of a smart system. A smart system can include an energy source that can be a scavenger, can include an energy conversion subsystem to generate a constant voltage, for example, for your cell phone, if we're talking about a cell phone. Then we have a communication unit, a sensor, and a processing. So this is the highest level point of view regarding a smart system. This Smart system includes all the necessary blocks that we need to include in a complete smart system. And of course, all these blocks, from an electronic point of view, need to be heterogeneously designed, as if we had different, let's say, design teams. A design team for the energy source, maybe related to the chemical world, or the chemical reaction involved, for example, in the charge generation, or somebody else who is using energy scavenging, or other people working on directly on energy conversion, buck boost converters, linear regulators and stuff like that. Then, for example, we can have people working on analog amplification for sensing, somebody who is integrating some microprocessor, and of course some communication subsystem that can be a Bluetooth transceiver, for example. But as you could see later, I will see later, that can be completely different based on a different technology. And this can be interoperability. There must be interoperability in using one communication block with respect to another. Another important point of this is, of course, you can have a single system on chip, maybe a single chip which integrates everything, MEMS maybe, microelectronics and all this stuff together. Or you can have different boundaries, because all these subsystems can be integrated in different technologies, for example. For a company, it's very hard to redesign everything if they have discrete components, okay, to redesign everything on a single chip, for example, because this implied a huge cost, okay, and a huge investment. And one of the most important things for the co-design of smart systems is to include already available IPs, intellectual properties, and the capability of uniformly simulate them in a complex co-simulation environment, okay? This is an example regarding sampling versus event-driven approaches. Why I'm talking about this? Because it's like we are revisiting, more or less, we are thinking about the meaning of analog and digital, okay? Because as you might wish, maybe you want to you want to design an analog circuit, okay? And if you want to design an analog circuit, basically, we are referring to differential equation-based models, right? So you have some kind of differential equation models regarding, you can think about a capacitor, you can think about an inductor, you can even think about a memristor, which is one of the edges, components that people want to integrate to increase the memorizing density, because they are very similar to neurons in their behavior. They can implement neuroplasticity. But then, we are thinking about differential equations, linear or nonlinear differential equation, whatever. If you think about a microprocessor, why do you think that design, electronic design, and the revolution came from 30 years ago till now? Every 2 years, this is the Moore's law, or something like that, the transistors keep on increasing, right? And the number of transistors on a chip keeps on increasing every year. Why? Because we are talking about a different model, which is not necessarily analog, but it's digital, and it's event-driven. It is a model that can be thought about a level and a transition, okay? And now, what I'm doing here with these slides, as you may see here in this slide, we have a digital, event-driven functionality and an analog, or MEMS, at the same time, because with MEMS, we are more related to the analog world, since we are talking about dampers, we are talking about masses, we are talking about a lot of things that can be, let's say, implemented and modeled, let's say, using differential equations. Of course, as you may see here, what you can do is to uniform all this kind of, let's say, ticking, because time is a continuous variable, and what you need to do when you want to simulate is to update the step time of a differential equation solver, so that every picosecond, every nanosecond, depending on the accuracy you want to reach with the simulation, needs to be updated. Of course, considering the huge heterogeneity of systems and all the design methodologies that are tightly related to digital blocks, what people invented is this transaction level modeling, in which everything can be, let's say, modeled as a transaction that has a beginning and has an end. If you want, you may consider the time step of the differential equation solver using a transaction. And of course, a transaction can be kept compactly expressed in a language that can be differently implemented in one model with one simulation kernel or another, okay? So this is important because it's like you are refining a photograph. You have a photograph which is a pixelized image, let's say, and if you increase the resolution of the photograph, you make pixels smaller. And if you want to increase the pixel, the resolution of the image, you increase the megapixel, the equivalent megapixel of your camera, for example, what you're going to is a differential equation model, which is the one closer to the reality. Of course, these digital systems can be described using Boolean math, of course, but, you know, this is enabled only because they work under two saturated levels, 0 or 1. The world is not working like that. But what we need to do is to make everything uniform, okay? This is an example, as I was telling you before. You can think about something that can be, I don't know, maybe the routine, the execution of a routine of a microprocessor, the packet transmission of your cell phone with the Bluetooth stuff that is sending data, okay, to your A2P audio streaming on your car, for example, and you have all this information receiving data, you know, from your car and stuff like that. You have packets, communication packets. It's like me when I'm talking to you, okay? I'm talking to you using packets. Every packet, it can be a sentence. Every packet, maybe, can be also identified with a word, for example. And I put pauses between one word and another. This is exactly the same thing. But our work, which is related tightly to wireless communication system, is the extension of this event-driven paradigm also to wireless communication systems, in which every packet that is transmitted can be directly thought about a duty cycling packet or stuff like that. So if I say A and I put a pause of 3 seconds like that, the active time that I'm using to send the information is just the time required for me to say A, for example. For the remaining time, the system can be considerably shut off, okay? Shut down. Or now, of course, we talk about here in this seminar of a wireless technology which is suited to the event-driven modeling and implementation, which is impulse radio ultra-wideband. Impulse radio ultra-wideband gained research interests since 2002, because in 2002, what people did is to release the, let's say, radiation masks to everybody so that people could implement wireless transceivers that could operate without any license, unlicensed operation, in a particular frequency band. It's like people decided that you can use one particular frequency band for you to transmit data with your CB, maybe with your walkie-talkie. That's exactly the same thing. You don't need license. You don't need to pay fees, for example, to use a particular frequency. And this is impulse radio ultra-wideband. What is the difference compared to other wireless technologies? The difference is that impulse radio ultra-wideband can make use of pulses, very short duration pulses. And all these pulses can be considered very short compared to, let's say, a typical medium data rate transmission of 1 megabit per second. More or less the transmission you need to achieve with your Bluetooth, for example, so more or less that's the order of magnitude, depending on, of course, the bit rate and the quality you need to stream to your, maybe to your car or to your stereo, for example, compared to the time of the symbols required for the transmission, okay? We're talking about 1 megabit per second or stuff like that. We're talking about pulses that last 1 nanosecond or something like that, okay? And if we think about a pulse, and if you think about a digital signal itself, you have edges that in the lowest technology nodes can be very fast, around 10, 20 picosecond, even more, of course, because if you keep on shrinking down transistor dimensions, then what you achieve is a very high temporal resolution, of course, because all the parasitic capacitance can be considered very small, and so circuit can switch faster. Of course, what is our reasoning? Is to apply digital modeling on an impulse radial ultra-wideband system, okay? Of course, as I told you before, impulse radial ultra-wideband, based on the recommendation of the Federal Communication Commission, who decided what kind of UWB signal can be considered as UWB, a signal that at least 500 megahertz bandwidth, or a fractional bandwidth of 0.2. And of course, the use of short duration pulses can be very useful in certain applications, not just wireless sensor networks in which we transmit information from one node to another with very low duty cycling. I'm talking about 1 nanosecond over 1 microsecond, okay? I'm talking about a very low duty cycling, okay? But also for other applications. The other applications can be, for example, ranging and localization, because thanks to the use of short duration pulses, what we can do is to determine the time of flight of the pulses when they are transmitted from the TX to the receiver RX. Of course, if we can consider the delay given by the speed of light, of course, it's not always the speed of light, but can be something different, okay, compared to the medium the wireless signal is traversing, of course. We can calculate easily the distance between one transmitter and a receiver. And this is one of the most important applications of impulse radial ultra-widebands. Of course, this is not the only one. We have a lot of other kind of applications that are related to wireless body area network. And if you think about recent, let's say, portable watches, for example, if you think about many vendors, I cannot say, of course, what they want to do now is to put sensor all over just to get all the information regarding your health, and then send the data to a centralized system, and then the centralized system can send the data to a hospital, for example, if you're a patient. Or maybe just get information regarding your lifestyle so that they can advise you what food you can eat every day, considering, for example, your energy expense. So in all this kind of application, the most important thing is ultra-low power. And ultra-wideband is one of the most important technologies because thanks to the ultra-low duty cycling we can achieve with pulses compared to a narrowband communication system or a wideband communication system, as if we're talking about GSM phones, UMTS, or maybe your HSDPA you have on the cell phone to get, for example, data from Facebook or for WhatsApp, or just go to the internet. In that cases, of course, the transceiver is shut down for the time you're not using it, but the signal itself can be considered huge, okay, with an infinite lasting duration compared to a UWB pulse, okay? This is just to give you an idea what UWB is. The use of short duration pulses to transmit information, okay? This is what I was talking about before, the FCC Part 15 Subpart F mask that is used to say that UWB signals must be below that mask. Why it needs to be below that mask? Because UWB pulses, okay, should not cause harmful interference to the other devices operating in the same bands. And these guys, with some measurement, with some analysis, with some telecommunication analysis, decided that this is the correct mask to be used, okay? Of course, we have power spectral density levels. We are talking about power spectral density, which is EIRP, which is effective irradiated power, let's say, and you have limits that are depicted here in dBm, okay? If you want to radiate UWB pulses, you can do it in whatever band you want, of course, but you need to stay below this blue mask, okay? And this is an example of UWB pulse. As you can see here, we are going to 0.5 to 4 nanosecond where 4 nanosecond, to have 4 nanosecond duration pulses, you need to put some BPSK, some scrambling on the phase of the pulses, because as you might have studied, Fourier transform says that if, you know, with 4 nanosecond duration pulses, you have 250 megahertz bandwidth, more or less, but you can change the phase of the pulses so that, you know, in 1 microsecond duration, for example, the average spectrum is still of 100 megahertz, okay? So I'm not going in these details, of course, but just to give you an overview of what this technology can do. Of course, one of the very important things of UWB that makes UWB so unique and so challenging at the same time, even for the design of a transmitter, for an efficiency point of view, and even for the design of a receiver, for a power consumption and selectivity point of view, is that if you think about the masks I was showing you before regarding the maximum radiation power we can send to the channel, the wireless channel, the thing that you have around here, of course, we are talking about of order of magnitude less compared to ordinary wireless systems. If I'm thinking about a GSM phone, for example, so now I have the data regarding only to 900 megahertz. If I can remember correctly, it's 2 watt power maximum. It's maybe 1 watt or 2 watt, 20 or 30 dBm maximum power in a very small bandwidth, so that people can reallocate bandwidth adjacent bands so that they can send information not overlapping and enable different wireless phones to use, let's say, the same channel, but in different subcarriers, for example. Here we are talking about minus 41.3 dBm per megahertz, which is more or less 60 dB in power, which is millions, 1 million times less compared to the other devices. So it's good to send UWB data, UWB pulses, of course, but UWB signals average, from an average point of view, and also from a peak point of view, because the maximum peak is 0 dBm, which is even 100 times less compared to the others, of course, is much less compared to the other systems. Of course, it's like me. Maybe now I'm using a very loud volume, maybe. I don't know, I don't have a feedback in my ears to understand it. But of course, if I speak like that, so people won't be able to understand me, okay, right over there. But people in front of me, yes. Of course, this is a matter of path loss, okay, because every signal that traverses the medium has a loss. And of course, if we want to have a link budget, it means I'm sending some messages to you, and you want to receive these messages, we need to establish my volume and the sensitivity of your ears, for example, okay? Of course, from a receiver point of view, and this is why I was telling you before that it is challenging, what we need to do is to have a very huge selectivity, so your ear is good for any frequency you can have around. But of course, you want to isolate the pulses compared to the other signals that are interference. And the presence of interference can be very harmful for UWB, because maybe from your antenna, you can have a signal which lasts 1 nanosecond for 100 microvolt amplitude, while the narrowband signal can have an amplitude of 10 millivolt or 1 millivolt, for example. Okay? This is the challenging part. Okay? Of course, when you talk about modeling for UWB, we are talking about a channel. And of course, what are the impairments of a channel? Maybe you have heard about multipaths. Of course, multipaths are everywhere. Even if you go to the Death Valley, maybe you have some very huge mountains or stuff like that. Maybe, I don't know, to any place, okay? And you scream, okay? And then you can hear echoes around. And echoes are multipaths, of course. And this is exactly the same as it happens in wireless communication systems. And of course, multipaths depend on the frequency of the signal we are using. Of course, multipaths are higher. You know, the presence of multipaths is much higher for UWB compared to narrowband systems, for example. Okay? And it depends on the frequency as well. Now, since you understand that ultra-low power design is very important for your cell phones, for example, it's very important for any device you want to achieve here. you want to achieve with your design. For every device that can be implantable in your body, for every, let's say, device that can be used to scavenge energy from the external world and maybe be put in some part of your body just to get some information useful for your fitness, for example, for medical information and stuff like that. Of course, what needs to be done is time to market design. And time to market design, what does it mean? It means that a company needs to come out with a good idea, okay, and with a good product, not just an idea. Sorry about that. We're talking about product. We're talking about engineering. We talk about refinement. Design and refinement, it means you make a circuit, you make a system, you test it once, and then it doesn't work. And then you go one more for another chip or maybe another system, you design it once again, you correct some errors, and then some other error remain. So it's, let's say, a trial and error sometimes design flow. And of course, this is valid also for radio systems that take more or less 5 years to be commercialized. So the ideas that you can see from a research point of view now regarding wireless systems take 5 years to effectively come to the market, okay? When I'm talking about this, I'm talking about smart systems, I'm talking about time to market, I'm talking about development, I'm talking about also of different devices you have. The devices which can be the cell phone, maybe the device you can put on your shoes to feel the pressure you're applying with your, maybe with your legs, because maybe you have a disease in your leg and maybe you have, you have to work better. Or maybe you want to sense your blood pressure because maybe you have some kind of other thing. Or maybe, I don't know, you have some chip in your, like in your glasses to get some information, to read out something. Maybe the degree of enlightenment you can have every day, okay? Something like that, because maybe you have problems in your sights, okay? The fact is that there doesn't exist a single solution for every problem you want to solve. And this applies also for wireless systems. And with impulse radio, we are talking about 1 nanosecond duration pulses and bit rates that can be 100 megabit per second, 10 megabit per second, 1 megabit per second, or even less, 1 kilobit per second, because your blood pressure or maybe your temperature in your body is not a signal that varies so fast. You need just to send very few bits to the central station. And of course, we're not using a wireless transceiver that is capable to send megabit per second data. What we want to do is to design a wireless transceiver which is tightly optimized for your application. Because, why? Because your chip, your system that is used to sense your health status needs to be tightly optimized for this specific application, okay? Given this, one thing that is very useful for the design of, let's say, mechanical systems is hardware in the loop. Hardware in the loop, if you take a train, for example, they're using it for example, let's say, brake control or something like that. What does it mean, hardware in the loop? It means that you have an hardware that can be whatever thing with some actuators you have in the external world, okay? And you put it in the loop with some kind of control system, which is a PC, something like that, just to simplify, okay? But the point, which is very important for hardware in the loop existing systems, is that we are talking about constants, time constants of order of 100 hertz, 1 kilohertz, okay? Because you're talking about huge masses. Think about a train. Think about something big, okay? We're not talking about nanosecond duration constants. There are 9 order of magnitude difference, okay? This notwithstanding, the use of hardware in the loop can be very useful because you can correct the control system in real time, okay? Because you need real-time control so that you can use whatever algorithm you want to adapt to the external world, okay? The goal of the work we did in SMAC, and of course I gave you as IIT an introduction before with the block scheme of the smart system I showed you before, of course, is the introduction of hardware in the loop for impulse radio to wideband system design. You have a test bench, for example. in which you have an hardware. In this case, the hardware is the impulse radial ultra-wideband transceiver that can generate short duration pulses that is put in the loop in a control time system, okay? Of course, what you want to do is to put some wireless transceiver that is capable of radiating pulses asynchronously with any data rate we want to achieve. Because everything needs to be tightly optimized to the application, of course. But what we need to do, since it is very important to, let's say, design our transceiver before, some good hardware, some UWB transceiver in the loop, okay? Why? I was telling you something regarding the channel impairments. And if I talk about channel impairments, I gave you the example of multipaths. Multipath can vary depending on the objects you have around in the surroundings. Maybe if I have a UWB transceiver here and another over there, I have a PC here, and maybe the path loss we can have, and multipath is different, okay? So based on the physics you have around, this multipath can be, these are statistical, of course, they cannot be predicted in any operating condition, okay? That needs to be they need to be considered early design stages. And of course, this can be very difficult. And what we need to achieve now is to put the loop, the UWB transceiver, in some control loop. But of course, you know, this is what I was telling you before. What we have to do is to design something which is aware now at the first design stages, not using models, not using MATLAB, not using some gamma distribution function, some Sunlink key model, some kind of, let's say, log normal distribution of the multipath that statistically may happen, and run some statistical simulation. We want to achieve directly the design with the real channel, with some UWB TIX and with some UWB RX, so that in the design of your chip, your system that can be used in, for example, for biomedical application, that can be used in your car, that can be used in whatever place you want, we already include in the design some physical stuff. This is hardware in the loop. We're not talking a model of the channel, of the wireless channel. What we want to put is directly the channel in the simulation loop. This is hardware in the loop. Of course, this is another, let's say, example of UWB modulation. You see, I was talking about UWB modulation, and here the transceiver must be able to cope with all this kind of modulation. PPM, as you can see here, we modulate the delay between one pulse and another. The hardware in the loop shall be capable of pulse amplitude modulation. The hardware in the loop should be capable of on-off keying. It means we have a pulse, it means a 1. You don't have a pulse, you have a 0. Or B-phase shift keying, which means based on the polarity of the pulse, we send a 0 or a 1, a digital data. All these are digital modulations. We're not talking about an analog modulation here, but of course it's possible even with UWB. Of course, this is another example. As you might see here, this is a real measurement of the channel we had in the lab. As you can see here, there was somebody using the cell phone, somebody who is, you know, with this antenna, I could receive some, let's say, low band, sub-gigahertz, as you could see here. I have a sub-gigahertz band in which I can receive digital TV, below, let's say, below 1 gigahertz. Then I have UMTS. Then I have some noise, which is given, some other GSM phone. And then I have a pulse. As you can see here, the bandwidth is huge. And this is at the bottom of the slides. You can see a time domain measurement on what a pulse is and interferences. Interference is lower with an absolute amplitude, of course, can be, okay? This is not 100% true because it depends on the distance between the transmitter and receiver and, you know, the number of possible interference sources around. But of course, you can see that these interference are very long lasting in time because there will always be somebody who is using the cell phone statistically around you, okay? What we want to do is to put everything in the loop. I cannot simulate all this channel using a very complicated and very accurate model, because otherwise the simulation time that would require to me to design the system would increase too much, and to me would be too long to, let's say, design a UWB transceiver which is robust to all these channels on ideality, okay? And it would took me like 5 years, but now the world is getting faster and faster. Everybody wants to make products. They want to come out to the market with some kind of new idea to commercialize something. And now we want to be more efficient. And efficiency, it means that we need to optimize a system based on a specific application, okay? Of course, as I was telling you before, we are talking about an event-driven UWB. And with event-driven UWB, I am referring to a system that can asynchronously receive any kind of signal, of course, and we don't have a clock. We're talking about a non-coherent receiver architecture because, of course, this is not necessarily true, but the work we did here for UWB implies the use of non-coherent receiver architectures, which means that are just energy detection architectures, of course. And this is an example of asynchronous UWB transmission. I have some kinds of UWB signal that must be sent. I have a trigger signal, which is the TR signal at the transmitter. I send the data. And at the receiver, what I receive? Toggles, right? It's like digital. Think about, for example, the transition of an edge from, of a digital signal that goes from 0 to 1. Every time I have an edge, I associate it directly with a UWB signal, okay? And so I can encode any kind of digital signal. Of course, the channel is statistical. Somebody is speaking next to me louder. You cannot receive my data. You cannot receive my voice because somebody is corrupting the channel with some kind of noise, for example. Here's somebody outside here just scream now. Of course, your attention will be toggled to this guy. And so we are not receiving anymore what I'm telling you, okay? Of course, what we can do is to transmit this data. Now, of course, if we want to think about the hardware in the loop, and this is a general extent, of course, you need to learn, because this can be very interesting. Given the capabilities that, for example, solutions like Arduino or other embedded system development kits are giving you, if you want to include the hardware in the loop, and I open a bracket once again, why hardware in the loop is very important? It's very important because you are enabled not to model the reality and put it in the loop, okay, and put it in your simulation loop, okay? Of course, you need to identify the hardware. You need to identify what the loop is. You need to identify the control system. And you need to understand why you're doing this, because maybe it can be a stupid idea. Of course, if you want to apply hardware into loop to anything that comes up in your mind, of course you can do that. But maybe this cannot be effective for the specific application. Of course, we want to apply hardware in the loop for UWB signals. Why? Because we have a transceiver that is event-driven that enables us to consider this hardware in the loop control. Of course, to do this hardware in the loop, you have to consider enable technologies. And one enable technology is UWB from this point of view. Of course, as you can see here, what we want, I'm going back just to one slide because, of course, I want to just stress out one more thing. Of course, we are talking about a hardware in the loop, right? And we talked about the control, right? Because I'm thinking about a system that needs to be controlled. Maybe you have to track the speed of your car. You have the cruise control in your car, you press your key, and then you forget about pushing the pedal, and just the car goes 100 kilometers per hour, and that's fine, right? And this is control, of course. What we need to do here for this SMAC, Smart System Co-Design, is to do a little bit more. Because now I have to clarify, maybe it was not clear before, that we're talking about design, because our project is about design. Smart System Co-Design. And what I want to do is not just to implement a control system, okay, with the hardware in the loop. Of course, we're talking about a wireless channel in the loop, plus a UWB transceiver in the loop. But what we need to do is design. So what we need to do is not just control, but to give the input of your VHDL simulator directly from the external world. You don't have a test band that generates for you input data. You don't have a test band that generates for you statistically with some kind of, let's say, metric that is close to the reality, some kind of correct input stimulation that can be real compared to your application. What you can put inside the simulator you're using for designing your system is just the real data coming from the channel. It's reality what you can get inside this, okay? And of course, what we want to do is to design a wireless transceiver, the processing part, the transmission part, okay, and the duty cycling control part as well, why not, okay, to shut down the transceiver when it's not required. You don't need to send data anymore, and the receiver shall not receive any more data from the channel because all the data is being completed, using directly the hardware, the channel in the loop with UWB, okay? This is the goal, okay? Think about a commercial tool you may use to design, for example, a digital block, okay? Maybe I'm thinking about some vendor you might have in mind, of course. You can use it. You simulate your VHDL code, and after you simulate your VHDL code, you go to a synthesizer and you synthesize it. Then when you have synthesized it, you put it on the embedded system, and then you run some validation with physical measurement. Of course, you have to install also the wireless transceiver. Maybe after that, you come out with the fact that your digital backend and the digital front end are not good because you need to redesign it somehow, okay, at the beginning. So you go to your boss and say, okay, I got something wrong. I'm very sorry about that, but there was something that I did not consider, okay? So you go back for another tape out and something like that. Of course, you can do it maybe in a research center, not always because, of course, this is not good, but in a company, you're not allowed to do that so much. What we want to do here, then, is to insert the channel, okay, and the wireless transceiver in this loop. With this kind of hardware in the design, you are sure that if you design some digital stuff and you test it all around, maybe you can test it here in your shoe, and maybe you can put it here as a microphone. You test it, you connect to a PC, and you run your VHDL model on that, you are sure that you're receiving data correctly. Maybe with this kind of application in which I have the shoe and maybe the other transceiver here for some reason that I don't know, okay, maybe we can discover that the gain of the receiver can be only 50 dB, not 80 dB, for example. I'm just putting a random number for you to understand. If I have 50 dB of gain, instead of 80 dB of gain, of course, the power consumption of the front end, when it's on, it's lower compared to the case of 80 dB. Well, I'm talking about optimization, okay? If I have one transceiver on top of this room and the other one on top of this room, but in the opposite corner, that maybe we don't have so many multipaths. Maybe we don't have to process, let's say, this kind of thing, right? We can skip the processing of multipath because the specific application does not want it, okay? This, of course, is what we want to do. As you can see, you have a digital hardware. We have a transceiver and a transmitter 1 and a transmitter 2, for example, and we have a receiver. We can also do some kind of multi-user tests. Because one of the most important things for UWB is to guarantee multi-user access, of course. We have very, let's say, very long off time between one pulse and another. And maybe you have to coordinate all the nodes so that during the blanking interval of one transmitter, everybody can send some data. It's like me. If I say one word of this seminar, somebody else can say another word of another seminar. And if your mind toggles from one seminar to another, you can get throughput of 2. if we talk at the same speed. Of course, this can be a stupid example, but just to give you an idea of this communication paradigm, okay? So, the digital hardware using this hardware in the loop, hardware in the design methodology is the thing that needs to be designed, okay? Of course, we have some advantages that may derive with hardware in the design flow. So HIDF, we call it hardware in the design flow, but I'm not going exactly very precisely on the terms because I don't want to, let's say, go with a lot of details. I want to, let's say, to give you the, let's say, the main message, okay? The main message of this hardware in the design, okay? Of course, we have different, let's say, advantages regarding that, and one of the main advantages is flexibility, because of course, as I was stressing you out before, so the transmitter back and front end and the receiver back end parts can be designed based on the application, okay? So take a look at this. This is an example of hardware in the design flow. Maybe you have a spacecraft that is approaching another, maybe base station. I don't remember, this is satellites, or maybe is it the European Space Station? I'm very ignorant, I'm not sure. But I took this picture just to communicate to you the following thing. So, we can design something even in this scenario. For example, every time you have some kind of object approaching a space, let's say a spacecraft or something like that, of course we need let's say a backend system that operates not to collide. Maybe we can understand here, and we can in real time simulate the channel that we can have here on the space, because on the outer space, because we can put all this stuff together, okay, and maybe design with your PC, okay, directly in the European Space Station. Maybe this is maybe a little bit visionary, but it's just self-assembling, fast prototyping on maybe an European Space Station, because we want to develop something like that. Okay, one of the objects that they had during the years is just to give the astronauts the capability of building themselves some parts that need to be used for missions and give them autonomy, so that they don't have to go back to Mother Earth, but just travel to Mars. Okay, and keep on going there. Okay, without having to replace parts on the spacecraft maybe and come back to the Earth. Okay. Of course, here, the hardware can be designed, for example, here you can see flexible. So that's a basic thing regarding hardware in the design flow. Of course, I'm not going into detail, but if you take a look at the literature regarding digital flow, what you can have is something, okay, you can design using a standard approach. If you think about here, I'm getting close because I want to see. So we have design constraint. The first thing you may consider for the design of something. And you guys need to consider this for any kind of engineering job you need to do in your life. Is what you need to have constraints. Constraints are most of the times, okay, application driven. They depend on the application. After that, for a digital system, so I was telling you that we want to design digital subsystem for this wireless transceiver, and I'm referring to a digital paradigm for design, a digital flow. You have the register transfer level network, in which you run functional verification with the tool. Then what you can do is to do some synthesis, you do some pass layout, and then you can do layout generation. You go to the GDS, which is a database which is used to tape out the chips and then send it to fabrication. Is basically, you should know what the GDS is, an ensemble of rectangles that can be used for layering, for generating some kind of negative images. They can be used and reduced with laser, okay, and to print out something monolithically on a circuit. Of course, this is just a file format. It's not it's a, let's say, worldwide known file format. But then, the most important thing is that you have to verify the system after that. You need to measure some data, okay? And as you can see here, what is the modification you can have on the standard digital flow using hardware in the design flow? Is that some part of partial verification? Partial, I'm saying partial. I'm not saying that what you do exactly on the simulator, on the design tool, is going to happen exactly, okay, at physical level. But of course, we enrich, okay, the description of, and you know, the validation of the first part of the design using this external, let's say, channel impairments in the case of wireless transceiver. Of course, okay, we have to generate events and get this data here. Of course, we have this, we are talking about prototyping, and fast prototyping can be achieved using FPGAs, right? You know what an FPGA is? Yes, everybody knows about that. And also everybody knows, everybody knows about Arduino maybe, for example, and of course the use of microprogramming platforms to do something and test, okay? Fast prototyping, I want to achieve a result very fast. And of course, this kind of hardware design flow, it doesn't need an FPGA to be co-designed. This is, let's say, it's weird because if we think about SMAC, it's not a direct co-design. This is something more than co-design because this is hardware in the loop. We are co-designing with a real stimulation that real time, I'm saying real time, come from the external world, okay? Now, I was telling you, okay, these are some kind of constraints we can have for digital hardware. Of course, digital hardware can be designed synchronously or asynchronously, of course. And then if you design synchronously with using different clock domains, then you can synthesize you can synthesize one block or another block and then put them together. Of course, there are also design tools that are not very known and very used in the industry that are regarding, let's say, asynchronous design. People think that asynchronous designs can be very useful. Still, even if everybody abandoned them to go mainly for synchronous paradigms, but of course, they exist. And, you know, this can be, it's just a matter of using some, let's say, terms. We're talking about a digital design, but a quasi-digital design, most important, okay? And of course, I was telling you constraints. And when I tell you constraints about this UWB-based HIDF design, I'm talking about basically the delay between one pulse and another. I was telling you delay, right? Why? Because if I send data, as you may consider one of the previous slides I was showing you some, let's say, modulations. The modulation of UWB are basically time domain based. They're based on a delay. It's like, I want to send you a 0, and I send hello, 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 hello. I want to send you a 1, hello, 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 hello. So, based on the delay between one pulse and another, you can understand that I'm sending you a 0 or a 1. And of course, the constraints that come out from this hardware in the design flow are delays. And so, we need to ensure that the design tool can handle these delays, okay? I was telling you transaction level modeling, register and transfer level, of course, and ultra-low power operation. These are the key features. But of course, I want to be more specific on the implementation. I just want to go further just to show you what needs to be done from a software infrastructure point of view to enable the real-time transmission of pulses and the real-time reception of pulses. Because the delay needs to be conservative. We don't have to put some latency. We don't have to put some processing latency. Otherwise, the hardware in the loop doesn't exist. Everything needs to be real time because exactly the same physics that come out with the channel needs to be exactly encoded and sent exactly to the design tool so that the digital logic can process the delays you have in receiving the pulses from the channel exactly with the real time, the real data coming from the wireless medium, okay? Is it clear? So we need to be real time. And with UWB, event-driven UWB, what you need to do is, what you need to achieve is real time processing. So basically, what we want to do, of course, we need to interface something, right? Imagine you have a development board in your USB. You connect it to your PC. You have a transceiver over there. You have another transceiver over there. And of course, you run your simulation tool. and the design, of course, simulation and design, because you know simulation is one thing and design is another thing, but of course without a simulation tool you can design nowadays, okay? But you know, what you need to achieve is this kind of real-time interfacing. We can go for an online interfacing. What does it mean? It means that from an operating system point of view, because you're running a design tool that runs over an operating system, the operating system runs on a specific general purpose PC, and then you know you have infrastructure for real-time capturing of data, okay? We can have an online interfacing, okay, in which the physical time, okay, besides latency, it can be a combination logic, let's say delay, more or less, and latency needs to be fixed, otherwise if latency is not fixed, has no use, okay, is matched to the simulation runtime, okay? This is one option. What does it mean? You send a packet, or a pulse, or whatever you want to pulse, real time, using this online interfacing. I mean, you don't send, let's say, some kind of string on data and that's it, okay? Everything is keep on going, keeps on ticking all the time. As you can see here, for example, you can have to consider all the latencies of the PC. You have to consider the latency of your USB interfacing. You have to consider the latency of the UWB transceiver as well. You have to consider all these issues. And of course, you have a maximum firing rates you can use with these pulses to, you know, not to overcome to the limitation of all this hardware that needs to be considered. Or you can go with an offline interfacing in which you stream, you save some buffer of data, you send it offline to the USB PCB, maybe, okay, USB interface where you have the transceiver, and then with a precise time reference, you just run the transmission of the data, and at the same time you receive from the other PCB, from the other module, sorry, I'm just saying PCB, but of course it's not talking about PCB, we're talking about modules. You get the data out from that, and then you combine it with simulation, okay? So one thing is online interfacing, and the other thing is offline interfacing that needs some buffer. It's like you record a song, and then you leave it off there, and then you play somewhere else, and then you record with a microphone what you are receiving, maybe in your room because you want to diffuse the music the best, okay? Something like that, okay? Is it clear? This is the timing example of the offline interfacing. Of course, one drawback as the offline interfacing is that you don't have typically a lot of buffer to save all this data. Of course, I was telling you online interface and offline interfacing, but all this, let's say, techniques we developed for the hardware and design flow need to consider basically the output, the standard output the design tool provides. For example, a design tool under VHDL, they provide a specific file, okay? They provide a specific file with the timing of the signals, okay? So these files are used to implement this offline interfacing, for example. So you can see that there is a lot of layering to enable this kind of hardware in the design flow, or to do some kind of real-time stuff, okay? And all to enable the wireless channel to be considered in the loop. Of course, you may think about online interfacing, in offline interfacing, okay? And you may consider that maybe the application, if you go for an offline interfacing, you transmit now, or maybe you transmit later, but of course, the statistics of the channel change, okay? Of course, this is a slide that shows you what does it mean, co-simulation with HDF. Of course, the interfacing of the external channel with the co-simulator, okay? And then you can co-simulate the hardware, the channel, and the digital, okay? Of course, if you put some reconfigurability and flexibility to the wireless transceiver as well, you can design also the wireless transceiver as well, okay? I'm not going into details on that, but of course, If you are interested, I can send you the paper, of course. You can find it on the IEEE Explorer, of course. But this can be promising for the design of wireless sensor network. Imagine you have some kind of flexible radio, not necessarily UWB, but pulse-based. Then you can choose a different frequency and you can design in the loop. And maybe this can be good for academic purposes because it can be good to understand the difference between a sub-gigahertz communication system and a gigahertz order communication system, okay? Of course, these are some advantages of hardware in the design floor for wireless sensor network. I kept on stressing them out here previously, but here you can find a summary because you were always talking about specific optimizations. And specific optimization derived from the specific application domain we are referring to. Okay, this is what we did till now regarding this hardware in the design flow. And of course, you can see you can see the antenna over there, which is the orange antenna, which is a high band antenna. Of course, a wide band antenna. Of course, we have a transceiver in one PCB and the other in another PCB. And what we do is to put this kind of interfacing, okay, with the ADA tool. You think about connected one transceiver and the other to for example, a development kit. This development kit can be connected directly to a VHDL simulator and VHDL development tool. Then you press a key, and then where you see the simulation running, okay, with offline or stuff like that, but the data you come with the input of your simulator is exactly the channel over there. You want to see what happens with, for example, your cell phone. Maybe somebody is calling you, and your telephone is ringing. You put your telephone over there, okay? You let somebody call you, and you understand the implications of interference in the bit error rate, for example, of your transceiver. That can be very useful, okay? Maybe you have a packet error rate of 1 packet out of 100 where nobody is calling you. But then if somebody else is calling you, you may discover that you have a higher packet error rates. And this is an example. We wrote here towards implementation because, of course, we need to work more and a lot towards a final prototype that can be used in any kind of application. Okay? Now my talk is concluded. I hope I sent you the message, okay, with some kind of packets, duty cycled packets. Hope that the average energy I used for you was not too, let's say, not too boring. I was not boring, okay? But basically, to summarize, what's the message here? We need to go with a solution for fast market, explorations of commercial products based on wireless communication systems. What we need to do is to fast prototype, okay? And to do that, we use the impulse radio ultra-wideband technology directly in the loop of some kind of design flow. We use it in the loop of a design flow. And of course, we can discover some implications for the real implementation of such hardware in the loop design. Of course, we're not talking about control as I was telling you before. Of course, why may I consider that given the increasingly specialized fields in which engineering is focusing, if you go for RF design, you're going to be an RF designer all your life. Maybe, maybe not. If you go for digital, you're going to be a digital designer all your life, or maybe not. Or maybe some kind of flexibility between one domain and another. But for sure, people is specializing on the implementation of, let's say, specific solutions. And of course, if you have a wireless transceiver, maybe Bluetooth, you can use in many different application domains. And now, smart systems maybe, or Internet of Things that is getting increasingly interesting during these days, the approach there for the design is modular. It means I'm going to use a Bluetooth transceiver in any application. And what I'm going to do is to use this modular approach, and for the application A, I write a code on the microcontroller. For the application B, I write another code on the microcontroller. And of course, I implement all the layering on the OSI level, you know, OSI stack interconnect and stuff like that regarding the layering on the services of any system. Of course, I can go for this modular approach because people is providing more and more, let's say, solutions that are increasingly low power optimized. But of course, if you want to go for low power design and maybe to get some cross-sectional, let's say, design exploration that can be useful for maybe from some application domain or another, we can go for this other in the design flow, okay? This last, let's say, comment was directly referring to, let's say, the recent trend I could consider on Internet of Things, for example. So everybody is doing perfectly their job and they're just connecting together with the modularity. The question is, the very important question is the following. The very important question. How we need to decompose, how much we need to decompose our picture with pixels? We need 16 pixels by 16 pixels? We need 256 pixels to 266 pixels? Till what level modularity needs to be explored? With this hardware in the flow, what we want to do is to give the designer all the flexibility that needs to trim this, let's say, decomposition of modularity, so that the design can be effective. So thank you for your attention. I hope it was interesting for you. Do you have questions? So the question was, is it possible to include a MEMS in the co-simulation flow enabled by HIDF? Of course, the answer is yes. We can include the MEMS. And I can give you an example where MEMS really matters in the design of a wireless sensor node. For example, if you have a lot of nodes all around, like you are 50 people around here, and I can, you know, tell you just to give me the data with a beacon. I can send you a beacon and tell you, okay, now just give me your sensing data now with a particular order given by, you know, the number of nodes you are, your identifier node. Then, you know, you can, if you don't have a very good oscillator inside, and an oscillator inside can be maybe implemented with a MEMS oscillator, then you can have drifts. And this impacts on the energy of the wireless link, because maybe I can receive, let's say, the information of node 20, 21, 17, 3, 15, and so on, but not all the nodes. So if I just receive the data from 5 nodes, then I have to shut down everything again and resend you the question, please send me the data again. And this implies to you to use energy for transmission, to use your voice, maybe, for example, like me, and just ask you for, again, just send me the data once again, okay? Of course, the implementation of hardware design flow with an heterogeneous set of, let's say, blocks, for example, a MEMS, or it can be also a microfluidic system, or it can be an optic system at the same time. This implies putting together, okay, different simulators, and of course make the simulator talk using, for example, system calls, for example, using dedicated interfaces, and so on. But of course, this is very important. So with this hardware in the design flow, of course, we refer to the inclusion of physical non-ideality in the loop. But of course, we can include any other kind of co-simulation at computer level. We interface one simulation and another in the same PC where the hardware in the design flow is installed.